Hello everyone. I'm very glad to introduce our topic about flexible fabric pressure sensory network based on the improved KNN. My name is Jialin and my teammate is Shangyan. So first, let me introduce our marvelous device and explain why we were inspired to create it. As we all know, flexible electronic devices have always been a hot topic in research, offering advantage that conventional sensors lack. They are no longer just code in personal electronic circuits. Instead, they can be deeply integrated into everyone's life. They cover a wide range of applications, and we are particularly interested in the more traditional pressure sensor devices. Conventional area sensors have many limitations, such as sensitivity and constraints in application conditions. We can see from the right figure, this is a traditional area pressure sensor. To address these issues, we propose a general area graphene sensor fabric, characterized by a linear electromechanical response. It remains stable under repeated stretching and moist conditions, maintaining high sensitivity and rapid response at low energy consumption. By measuring the voltage output changes caused by the pressure and using machine learning algorithms, we can accurately determine the pressure points and achieving pressure localization. Here's our distribution and innovation part. I am responsible for the circuit design, device manufacturing, circuit simulation, and data acquisition. My teammate is responsible for the data processing, algorithm optimization, and result analysis. Our project have many innovations. First, according to the characteristic of flexible fabric, a resistance network model is established, and the feasibility of the model is verified by simulation. And we also propose a pressure sensor for natural wood fabric, which has the characteristic of fast response, high sensitivity, and low energy consumption. And its feasibility and stability are verified by the experiments. And also we use a powerful tool called KNN to organize thousands of data and make decisions. And the steps that can be optimized in the implementation of the algorithms are improved to different degrees, such as feature engineering, simplified calculation, etc. And the new decision-making strategy, KNN attention base, is proposed, which successfully improves the recognition accuracy. So when it comes to the material and simulation part, uh, the graphene diode we use in this project, it blending the traditional comfort and appeal of woods with this magic graphene material. It has tremendous physical features such as electroconductibility, high fabric durability, water and strain resistance, thermal conductivity. All this cutting-edge benefit uh, will have a great potential market in the flexible sensor. And we make cadence simulation with a simplified circuit, and we can see from the right figure that when we give a pressure on different areas, we can always have different voltage patterns as output. So we can say it is possible to determine the pressure points through the change of 3 voltage output. And then we make our next step.
So here are the improved steps of KNN. Feature engineering is the process of transforming the original data into features that better discover the problem so that the application of this feature into the prediction model can improve the prediction accuracy of the invisible data. So in this design, in one time window, four time domain features are extracted respectively for V1, V2, and V3. After factoring, each sample has 12 features. Then two feature engineering methods are combined. Firstly, we use the low variance filtering method to select important features. Then the PCA was used to reduce the feature dimension. By doing so, it can remove invariant information like noise and identify hidden patterns in the dataset. And for distance calculation, can generally use Euclidean distance, but it is easily affected by the sample distribution space. The old solution is to use the inverse of the distance for weighting, which fails to consider the dimensionality of space. So we use cosine similarity for weighting instead. It can reduce the high dimensional influence of Euclidean distance. Moreover, it can also reflect the relative distance difference in directions between features and is more effective in adapting sample distribution. So in this design, a new decision-making strategy model can attention bias is proposed. The attention mechanism is a new kind of deep learning network processing rule. It generates a sparse matrix of weight to sum the input of the object and identify the importance of the input object to the training object, which minimize the interference information of redundant parts to improve efficiency. The samples of the same kind among the k-nearest point act as key and value, and the test samples act as carry. And output finally obtained is the attention that should be allocated to this kind. And for knife bias, because the feature are continuous values, we assume that the conditional probability distribution of the feature conforms to the Gaussian distribution, and it assumes that each feature in the sample is independent. For a given sample to be classified, the test sample, a posterior probability distribution of each class is calculated using the nearest k training samples. And finally, the result value is gained by multiplying two values calculated above, and the class with the largest result value is regarded as the prediction class. And for setup, we use 10 and stack model to place in 9 areas randomly. Three voltage values are continuously collected 400 times as one set of data in 20 seconds. For preprocessing, the peak post data and unstable points are removed and replaced by the overall average values to enhance the data. And so we collected 50 sets of data each. As can see, the preprocessed data has good concentration, and the result is in line with the previous simulation. Next, we conducted 3 sets of comparative experiments on KN, including different PCA dimensionally reduction dimensions, weighting method, different weighting method, and decision strategies. So the basic idea is to compare 3 situations: the underlying model, the existing approach, and our approach. It can be seen that the performance can be improved by using our method, which proves that our method is better. For example, for distance calculation, the gray bar is higher than the rest of the bar, which is our method. And for decision strategy, KN attention bias is better than the other two models. So based on the above 3 experiments, we got the optimal model and drew a confusion matrix diagram of the optimal model and the performance chart of each classification. As can be seen from the confusion matrix, the accuracy of all classifications is higher than 95%, with 3 regions 2, 4, and 9 reach 100%. And for the performance chart, the advanced performance reached 98%. And like the confusion matrix, region 1 and 5 are relatively poor, but it is totally acceptable. And that will be all. Thank you for listening. If you have any questions, just post it on the piazza. Thank you very much.